Thank you, Fiona, and thanks also to Isabel and the other members of the organising committee for giving me the opportunity to speak. And actually, in terms of that introduction, which was really very nice, but just one further point, I'm actually a graduate of DIT, DIT originally, and actually came through here through Cavan Street in terms of my degree in chemistry. So in terms of my presentation, what I want to do is actually three main areas. One is additive manufacturing, this 3D printing piece and applying metals or printing metals. The second aspect is looking at the diagnostics in terms of that, and also in terms of capturing the data. So in many ways, in terms of the workshop, it combines a number of elements of that workshop. But before I start, I just want to introduce my day job. My day job per se is directing the I-Form Advanced Manufacturing Research Centre. And maybe just to explain a little bit about it, essentially it was started in November 2017, and as you can see, the focus is very much materials processing and capturing data. And if you look at the top line just over the images there, you can see what we would normally do in terms of science or engineering in terms of materials monitoring and capture and taking data. But what we're doing is trying to combine that with the data side, looking at data analytics, looking at what's cognitive computing, this ability of computers to understand the sense which we're asking them, but also to feed that information back to operators. And it's all part of what we call Industry 4, this rapid change in manufacturing where the digitalization of manufacturing is occurring, and we're helping to address that. At the moment, the centre has about 35 researchers, and there's a 27 group in terms of the academic team. So, as I said, my presentation is on work we're doing in metal additive manufacturing. It's not very clear here, but basically there's a laser moving across a powder bed here. That laser is heating up the metal, melting it, and essentially we're getting a layer by layer deposition. Each layer is about 30 microns in terms of its thickness. And what we're doing is using this technology to print medical devices. Now, Ireland is actually very strong in terms of this technology. Companies like Stryker in Cork would be one of the world leaders in additive metal, for example, and they make knees and also spinal devices. And why is it used in this way? Well, firstly, it can be extremely difficult to make these devices by conventional machining means. Secondly, in terms of their surfaces often have really rough type morphology, and that's because to allow cells to integrate with them. But over the last 5 years in particular, there's been a transformation in terms of sectors associated with this. On the top right there, you can see a dental implant. And in many cases now in the UK, you go into a dentist, they'll scan where you have a cavity in your tooth, and they'll actually send it off that scan. A print will be made within 2 days to come back with an exact individualized implant for your mouth. So this area of individualization, tailoring, the ability to produce complex shapes, the ability to tailor surfaces, and to do it in a single process are some of the reasons why additive technology is taking off. The image up here shows a typical print bed after the printing process. It looks like something like a sandstorm has taken place, but essentially what has happened is those parts that have been melted by the laser, essentially you see them, you take them out. There's a lot of cleaning and post-processing that are used. As I said, in this case, we're working in this titanium alloy, titanium aluminium vanadium, which is a biocompatible metal. And what I want to do in terms of this presentation is to fit the description of it in terms of the physics, data science, and health. And well, environment is also related to, because environment fills in terms of all these areas. And to highlight this in terms of work we're doing in printing of these metal alloys and how we're capturing data and using that data, we hope to use that data in terms of predictive process control. So with respect to the parts that we're printing, that's a typical build plate there. Now we're working with, it's a production scale metal additive system. It's about 25 by 25 centimeters. It's a powder bed system like the one I showed you in terms of the short video. And each of these parts here, as you can see, they're 15 by 15 by 28 millimeters in size. And we are printing these, cutting them down slightly to make them all even, and looking at mechanical performance. And in this study, what we have been doing is to look at the laser energy, the impact of laser energy in terms of the melting powder, and to see the effect that has. So you can see that the laser power goes between 50 and 250 watts, and we're looking at that. Now, as you probably would expect in terms of a lattice structure, if you put more energy in, you'll get more melting, and that's what we see. You see a consistent decline in porosity as the more energy goes in, because the strut sizes become a little bit wider. These strut sizes vary from, they're about a quarter of a millimeter, so they're around 250 microns. In fact, when we look at the sizes, the smallest size we get is 235, and it goes up to 292 microns as the laser energy in the range that we're looking at is increased. So we get this consistent change in terms of it. So once we've actually printed the part, the next step is to evaluate its mechanical performance. And in this case, what we're doing is crushing them and looking at the resistance to that crushing. And you see the old fracture in similar manner. And what we're again seeing, this broad consistency where you get an increase in mechanical strength as the laser power is increased. There's probably one exception there, this FOD, which is the focus distance, has been changed where the slope is slightly different. But in terms of just laser energy alone, we're seeing that consistently. But in terms of a process like this, the laser energy alone is only one element. And if we're making a medical device, it has to be consistent and right first time, every time. In terms of conventional manufacturing technology, for example, machining, you might make 1,000 parts and take a number of those out for testing. With additive manufacturing, it has to be right first time, every time. And to achieve that, what you need is a really deep insight into how the manufacturing or the process behaves and how we can actually diagnose that process. The bad news for additive is that for the most part, the sensor arrangements haven't been as well developed because it's a relatively new technology. But what I want to do here is talk about one example, which we're fortunate to have with this Renishaw machine, which is the first example that on a production scale manufacturing system for in-process monitoring. Why is it important? Because when the laser comes in, we melt the powder. You produce what's called a melt pool. That melt pool is about 35 microns in diameter. And the laser moves along, the melt pool behind it cools, and the next area heats up. But if the melt pool is slightly wider or slightly smaller, it will change the area, as you saw when we actually treated the struts. So the stability of that melt pool is critical, and understanding of its behavior and performance is vital in terms of it. Why? Because if you consider an additive manufacturing process, it's layer by layer. If you have too much energy going in, you can overmelt the area. You can also cause pinholes or drops or air bubbles inside in the structure. You also have issues around compressive stress, because what happens is that you can have an area that's very hot and an area that's cold, and obviously that would be a very, very stressed material. Quite often in this space there's post-heat treatments to anneal the stress out of the structure. Examples of stress are shown in the top left there, where parts are lifting off the plate as they're being printed. Another issue is if you have an overhang structure, quite often we want to produce holes in the structure. For example, where it tubes, for example, the spinal support, you need a hole in the structure in terms of fitting around the actual spinal piece. So again, there can be issues there of overheating, and so to try to monitor that. So I mentioned that Renishaw had allowed us to work on their technologies, the first system out from the company externally. And what it does is it does two things. One, it measures the energy of the laser. So you can see the laser view photodiode directly under the laser there. It's capturing that energy from the laser with a single photodiode. It also has a number of photodiodes working at different wavelengths mounted around the melt pool. And what it's trying to do is assess the energy of that melt pool to give us an indication of what's going on. So the question is, how accurate is that? and how good in terms of a system, in terms of reliability. Nothing has been published in that, so we were the first to get it, so therefore this was a great opportunity to allow us to investigate that performance. So in terms of the system, what it does is it gives you a color output. It's not quite kind of green, red, orange per se, but it's in that regime. So it gives you a color change. Red is overheated, blue is underheated, ice cold blue. Something in the middle, a greeny yellow, is probably in a good regime. So what we did is we started out by saying, okay, what sort of shape are we going to print in order to look at the thermal effects of the laser? And we specifically went for a triangular shape because you can imagine as the laser comes along at the very tip, it's likely to be overheated. We also went for a circular base on it because we wanted that energy to be dissipated more evenly. We printed with the range of energies, our laser powers that I mentioned. You can see the little spot size there. As I said, it's about 35 microns in terms of spot size from that laser. And what we did is we varied a range of powers. Each power was done under 6 different replicas of that. And we also looked at the effect of the mechanical strength versus those powers. Now, in terms of this, what we did is we took a single layer. So if you can imagine the little lattice structure, we took a single layer across that, about 300 points, added all the energies and divided it by the 300 to give you a homogeneous value, which corresponds to a single point here. And we plotted that against what's called a melt view, which is the energy from the melt pool, and the laser view, which is the energy from the laser view. And the good news for us is that we actually got a reasonably linear correlation. So therefore, taking the energy data, we get a good indication of the amount of energy that has gone into that surface. So as an in-process control, it does show considerable potential. So having established that, the next thing we wanted to do was, okay, what happens to the geometry? We now know that our laser energy can be correlated. Can we look at geometry and see how good or accurate the system is with respect to its ability to look at shapes? So what we did on the left-hand side there, we printed some shapes which are circular, some square and rectangular, and we printed them, I think there's 17 along the height of the part, and we consistently looked at those in terms of their performance. So what we get is this sort of image here. On the very last one, you'll see that the holes through the structure. So basically, we can actually assess the dimensions of the part using this spectral software in terms of in-process control. So how does that relate to the actual produced material? So we used a technique called computed tomography, which is an X-ray analysis technique to allow us to look at the structure of the as-printed parts and compare those structures with the printed part. So up on the screen behind me, the blue color is the type of data we get during the printing, this is in situ data. And it comes down to the resolution of pixels and the ability to capture the light from the material. The image, the gray image in the image is the computed tomography, the CT image. And the image on the left is actually taking the space and actually making it as a solid. So you can actually spin that around and look at the space. So we tried to correlate that. Interestingly, you can see some defects in terms of structures, particularly on an overhang structure. And part of that, as I'll explain in a second, is that you can get overheating, because if you have a powder and you're printing a very first layer of solid material on that powder, the thermal conductivity of the powder is less than that of a solid material, and you can get overheating, you get some melting of the powder below. So to look at the correlation then between the CT data and the data that we get in the process, we've got a graph like this one here. So it shows 3 things. The yellow line is what we asked it to do in terms of size, and consistently what it's done is actually printed slightly bigger than we asked it. And the reason for that is that our laser was stopped a little bit too short of the edge. In other words, we anticipated that the laser would heat and there would be a little bit of overheating to the edge. It didn't occur. So we would need to alter the laser's position such that it would go a little bit further to the edge of the sample to correct it. The most important pieces of data, though, are between the red and blue bar graph here. So the red one is the CT data, the data we get after the printing process, and the blue is the data we get during the printing process. And for the 600 microns, it's within 1.7% of it. However, for 200 microns, it's not close at all. The resolution just is not there. So what we're seeing is decreasing performance in terms of resolution as the size of the part or the whole being printed gets smaller and smaller. So that kind of shows the limitations in terms of technology. It gives a qualitative indication at the lower end, very much quantitative at a scale of about 600 microns. So the final piece in terms of the evaluation that we've been doing in terms of this process is that overhang issue, the printing of the very, very first layer after you want to produce that hole in the surface. And what you see on the left-hand side of the screen here is this yellowy color, and that's the very, very first layer of metal being heated up over the powder, as I said, and it overheats. And we've also been able to obtain the raw data. Now, generally when the system is being sold commercially, and it's only just coming on the market now, they won't provide the raw data, but fortunately we've been able to get this. And what we see in terms of the raw data is this continuity associated with the area which is overheating. So we've been examining this and say, well, how accurate can we obtain this data? So in order to look at this, rather than the lattice structures, we've been printing hair-like structures. These are about 1/4 of a millimeter in diameter. And you can see on the image on the top left that in some cases they curl over, in some cases they're very straight. And the good news is that they are consistent with respect to the amount of energy we put in, as you see in terms of the pixels and graph here. But the question is, can we actually assess what is likely to happen during the run in terms of that print? So if you take the scan on the bottom left, this yellow, you can see it's a very homogeneous scan, there's no noise. The one on the right showed the noise, and it was associated with a run for which there was some movement or distortion. So this would, if we could use some of this data as a predictor and say, okay, there's no point in continuing after you see X amount of vibrations or X amount of movement in terms of that intensity, this hopefully will allow us to act as a predictor. It's crucial, as I said, in terms of this sector, because if you have a single layer which is defective in a medical device, that's enough to cause catastrophic failure in terms of the performance. More broadly, within IFOAM, what we're doing is using the data captured from this system to try and inform operators what's going on. So working with DCU, with Alessandra, what she is doing is taking the data, the raw material that we're taking, it's actually video data, and taking that data to try and look layer by layer, such that we can feed it back using techniques such as augmented reality to kind of look at the defects, to provide a mechanism to understand those defects within the structure. So it's the ability of data analytics combined with techniques such as augmented reality to provide a direct feedback in terms of what's going on. Why is this important? Well, it's likely within the next 10 years we'll begin to see what's individualized devices. We're already seeing it in the dental area, but more likely in the orthopedic area, where the push will not be to, say, if you get a knee or hip implant, where it fits within different size ranges, it will fit exactly to your requirement. But in order to do so, it's likely that a lot of that printing will be carried out inside hospitals as opposed to in a large manufacturing plant that we've traditionally seen. If we're going to do that, however, there are lots of data issues that need to be solved, particularly around the security of data. The processing conditions obviously are very secretive that the manufacturers would use. Also the speed of processing and the systems around that, but it's likely with individualized manufacturing that in hospitals there will be a printing wing which will carry out print under very supervised conditions. So in order to achieve this is kind of part of what we call a cyber-physical production system. And this is expressed here in terms of a paper from 2015 where they talk about it in terms of 5 C's: connected, conversational, cyber, cognitive, and configuration. And what I would say in general terms is that what I've described here has very much been around the data acquisition from a system, the status and the tool delay to a certain extent. We've done a little bit of analytics, but what we're trying to do is combine them all together, but very much in its infancy. And it's an enormous effort involving multiple partners, multiple disciplines, even for one area as I've described in terms of these medical devices. The goal in terms of this example here is that, and this now is for a plant rather than for a process, but the same kind of focus applies, where you can have multiple outcomes. If you can predict what's likely to occur, can you alter a process, what's the degree of sensitivity of that process, and so you can use this as a way of controlling and execution what's going on, such that you can take measures in advance of something happening with the process to stop those problems arising. We're also taking a broader element in terms of this. This is an iPhone logo here. So or an image. What we're using to try to do this is that the human part of this is always going to be so important. The machine part, to a certain extent, can do it, but I think it's going to be very unlikely that a machine operated like a Renishaw will allow the degree of interaction with their equipment because of health and safety reasons. It will always go back through an operator, at least for the next 10 years. So informing the operator, giving the operator the information in a way that will allow them to act but not to overload them is going to be key, and how to feed that back. We talk about a book of knowledge, and they can look up information in terms of that process. So in terms of a summary, in terms of the area, the Infini-AM spectral technology has considerable potential, in particular in the area of looking at the size of objects, correlating the energy during printing with what's happening. Certainly in terms of our work, it does show that there is potential there in terms of the predictive part, and using this as a model for that introduction of a cyber physical system per se. Just before I conclude, in terms of the workshop's objective, in terms of broader engagement, maybe just to highlight in terms of my own work, I've one slide here just to indicate that. This is in conjunction with TU Dublin. It's in conjunction with Vladimir Milosevic, where we've been collaborating for at least the last 10 years on plasma and plasma processing. This is some work we've been doing in the area of developing what we call a barrel plasma for treating polymers, some of which is for use in medical devices. We've done work with a company extruding parts using polymer particles being activated. So the engagement with TUD, particularly with Vladimir with respect to optical emission spectroscopy, has been vital in terms of our deep understanding in terms of that process. So thank you for your attention. Certainly, what I can say is that it's routinely applied in the UK now. Renishaw itself have quite a business. I think there are 5 or 6 machines constantly on the go, just simply providing a service to dentists who, for patients who want a very exact fit. So it would never be a situation where the dentist literally might use a small little file to remove an edge off kind of an implant going into your body. It is printed exactly for what the requirement is. So it offers a much higher level of precision and right first time in terms of the patient. So it's an example of individualization which additive manufacturing gives. What I'd also point out is a second example, and maybe to illustrate this, there's another device, it's a polymer device in this case, called a cochlear implant, or cochlear implant for your ear, where again they would scan the ear and the implant fits snugly in your ear, as opposed to, yeah, it's a little bit sharp here at the edges. It fits the ear exactly. So that is the move in terms of this individualization in terms of devices. Yeah, it's what I would say is it's funny when you go to a company like Stryker. I mentioned that you go into a facility with enormous numbers of machines, and they would say to you, "Yeah, we actually have started this 10 years ago. We only got approval in 2012. They started around 2002. The level of work in terms of the deep insight is enormous. So the good news for engineers and scientists, there's a lot of research work to be done to actually get these processes up and running, because for each one of them, you need to know what variability you're allowed, and what changes in conditions. So there'll be plenty of work for us. Okay.